Okay, 7:33. Let's begin. Good evening, everyone. Start slideshow. Okay. We will talk about a little bit about systems of inequalities and just I have two simple graphing examples of those that we will look at, which you can see here. These will show two kind of special cases that can happen when we have systems of inequalities. And the other one and the other system of inequalities question, we'll look at an application, just sort of, again, a visual demonstration of what the possible solutions are for some situation. Those shouldn't take too long. And then after that, our focus will be excuse me, some linear programming questions. I have 3 here that I've prepared. A, these take a long time, and B, we haven't gone through all the linear programming questions examples in class yet. So I'm kind of thinking we'll do at least one of them. We'll see how much time we have. We might do a second one. Might be better to hold the third example off until next week. Next week, the main thing will be matrix operations and matrix multiplication, since that's the most challenging part. But we'll have time to do another one of these questions then as well. So spreading it out, we'll see how things go today. Okay, we'll just jump into this. I hope if you did want to have another look at these questions after the workshop, or if you did before, then you were able to find this textbook posted on our classroom page in the textbook information post. Next slide, there we go. Okay, so just graphing systems of inequalities first. I have these two here, and we'll see what we can do with them. All right, so the one on the left here, are we ready to go to a graph and try to graph that situation, or do we maybe need to do some preparation work first?
We need to do some preparation.
Can you say that one more time?
Preparation first, if it's just possible. Maybe we'll get.
Sorry, it's quite hard to hear you. It sounds like your microphone is blocked.
I mean, we kind of start with the preparation first. It will help us more.
Okay, what preparation are you thinking of?
Line equation.
These.
Subtracting.
Okay, can you a little more detail?
You mean that we need to do matrix for this one, right?
This is not a matrix question. This is we have two inequalities, and we want to represent the system visually. We want to graph these two inequalities and see what the solution space looks like. If someone else wants to suggest, go ahead.
First, we need to find the x and y intercepts in order to mark them on the graph.
Okay, so let's say the first one here, x and y intercepts. Okay, we could do that. So x and y, and what would those be?
4 and -6.
-6 here. So 12 divided by -2, that's -6. Okay, good. And then the other one, well, we could rearrange this and do like a 2 intercepts thing, but this is also slope intercept form. This is pretty, graphable. We can work with that. So looks like we're ready to graph the situation on the left here and see what that looks like. I am just realizing that's the graph I had set up on the next slide has the wrong sort of dimensions to it. So I will fix that quickly. While you're waiting for me, you can look at the one on the right and think about what we would do to graph that. Do we want to change the form? Do we want to find the intercepts? So take a moment and think about that, and then I will get this ready. Apologies here, and I did have this set up in advance. I just put the wrong thing on here. Okay, that looks better.
I'm sorry, Professor, may I ask a question?
Sure.
What do we do in the second equation? What does 12 over -2 mean?
Okay. I'll just repeat the process of finding the intercepts. So all right. So if we're going to graph things, the two simplest ways of doing things, if we have our slope intercept form like this, so y greater than or equal to 3 over 2 x plus 1, there's the slope, and there's the y-intercept. That's ready to graph. If we have standard form like this, 3x minus 2y greater than or equal to 12, then we could get this ready to graph by changing it into slope intercept form, or we could just find what the two intercepts are here. So the x-intercept and the y-intercept for this one. If we want to find out what the x-intercept is when y is equal to 0. So if we look at this equation here, when y is equal to 0, so 3x minus 2 times 0. So just basically the thing with the y is disappearing. So just kind of forget that. What's remaining? 3x equals 12. Okay, so x is equal to 4. X-intercept will be equal to 4. And if we do the same thing, but for y, then we just forget the x, and we have 12 divided by -2, the coefficient on our y, and that turns into -6. So this is just our quick shortcut method of finding x and y intercepts for an equation given in standard form.
Okay, thank you.
Welcome. All right, so those two are ready, and let's look at the ones on the left as well here. So the first one, we have a
we need to transform it again, like the -1 is greater or equal to 3.2x minus y.
Do we need to change it?
No.
No, we don't. It's it's slope intercept form. If we want the two to be similar, if we were going to do elimination, then sure, but we're graphing. So as long as we have a way of graphing each of these, so y less than or equal to 3 over 2x plus 1, there's the slope, there's the intercept. It's almost the exact same as the one on the left here, just the shading will be different. So that's ready to graph. We don't need to change anything. Again, like think about what the question is asking you to do, graph it. So that's ready to graph. The other one, we have
X is 4.
x plus 4y less than or equal to 4. So we want to figure out the two intercepts. Our x-intercept is 4 divided by 1, so 4, as you said, good. And our y-intercepts
1.
is 1, so 4 divided by 4, that's 1. Okay, so now we have both of them ready to graph. I might feel a little irritating to have them as opposite different forms here for graphing both of them, but I want to make sure we remember both methods of doing this. So let's take this over to our graph. I will move this all a little closer up here and our blue one. Let's just get this out of the way down here and we'll do that one next in a moment. Okay, so more color coding. Let's say we'll do this first one here in purple. We have our y-intercept is 1 here, and then our slope is 3 over 2. 3 over 2. So that means if we go left 2 steps for x, delta y over delta x, then we go up by 3. So we'll go through this position here, that point, and that's 2 points. We can graph the line from that. It's going to go down this direction to here. Like this. Okay. And are we shading above or below this line?
Above.
Above. We have a greater than or equal, so y must be greater. So everything above and to the left of this line is this feasible region. Sorry, just the solution area. I'm thinking in terms of linear programming terms. And our second one. So we have this 3x minus 2y is greater than or equal to 12. We have the intercepts for -6. So x-intercept of 4, y-intercept of -6 will be here. And we'll graph that line. Which will look exactly like this. And this one as well, are we shading above or below?
Above.
Above. Okay, good. So we are shading above here. Like this. Again, if we want to test this, we're not sure if we should be going above or below. Just substitute in 0, the point 0, 0, or any point at all. But the origin 0, 0 is easiest into the inequality 0 minus 0, so 0 greater than or equal to 12. Okay, and what do we see when we do this?
It's a false statement.
False statement. So what does that mean about our origin here?
Should be we should shade below.
Okay, so we shaded on the wrong side. We should be shading below this because our origin 0, 0 is not included. This is a common mistake. Sorry if you were taking notes and I'm making you rewrite it. This is a common mistake with these standard form equations. It can be a little bit confusing if we are shading above or below. It's sort of kind of, you can't just go by the sign of the inequality. It kind of reverses depending on what side of the origin you're on. So testing a point, a very good habit to make sure that you are doing the correct side here. So let's redo this, and we are shading below. Okay, so what do we notice? Now that we've done this, what do we notice about these two inequalities?
There is no solution
Okay, tell me why you're saying that.
because there isn't an area where the two inequalities can meet somehow.
Okay, so on the graph currently, for the area that we can see, there's no overlapping area. Do we know that there is, like, maybe if we go off like 1,000 units down here or up here or something, do we know, can we know if there is never any overlapping area, or can we only know about what we see right now?
There will be no overlapping area.
Why are you saying that?
Because the area they're covering, it goes to the infinity.
Okay, but the two lines, they could very slowly be coming together and then eventually cross over.
Maybe because the two lines are parallel.
Okay, how do we know they're parallel?
They have same slope.
Same slopes. So we can see the slopes here. So 3x minus 2y. The slope, let's write this as equals 12. Let's imagine if we were to rearrange this, it would be 2y is equal to 3x plus 12, and then we would divide everything by 2. Y is equal to 3 over 2x plus 6 here. Sorry, that should be a negative sign. Minus 12 minus 6. So here we see the same slope, 3 over 2. We could also see that right away in this standard form, ax plus by equals c. The slope is going to be negative a over b. So negative a over b is the slope, and we can see that here, 3 over negative 2, and then flip that sign, that's positive. So same slope. These two things are parallel. So they currently, in our graph, they have no area of overlap, and they are parallel, so they will never cross, so they never will have any area of overlap in either direction as far as we go. So this system of inequalities has no solution. There's no point on the graph where the two overlap. There's no point that is a solution to both of them. Okay, so there's our solution. That's one type of special case that we could have here. No overlap. All right, let's look at the second one that we have. I'll just give you a second in case you're writing something, and then I'm going to erase this. Our second case was supposed to show something. Oh, can't do that. Our second case was supposed to show something else, although I'm looking at the numbers right now and I'm not seeing it. So I just want to make sure I copied the right things off the textbook. So once again, if you just give me a moment, I checked the later questions very carefully, but I should have checked these ones as well. 4.7. This is question 4.116. There we go. Yes, I forgot to flip that one thing. All right, I will make a small adjustment and then we will look at this and see our second special case. That one's less than, that one's less than. Okay, that looks better. All right, apologies for that. So the first equation was the one where I had some of the numbers incorrect. But the work we've already done to find the x and y intercepts, we don't have to repeat that. And the first one, we can just graph directly here. So that's not really a big problem. Okay, so let's do that. Let's actually graph the first one. Let's choose pink here. So this first one, y is less than or equal to -1/4x plus 2 for our y-intercept is here. And slope is -1/4. So remember, positive slopes look something like this. Negative slopes are going to be sort of going down as we move to the right. And slope of -1 would be exactly like this, 45 degrees. And this is -1/4, so less than that. It's going to be something like this. Let's actually draw this properly. So delta y over delta x. Delta y over delta x, so -1/4. So when x goes over by 4, then y should go down by 1. So that's this position here, this point, and then this one here, like this. All right, and there is the line. Just trying to line this up. There. Okay, let's do the shading here first before we do the second one. Are we shading above or below this line?
Below.
Below. Okay, so slope intercept form, this one's easy to see, easier to see. Y must be less than or equal to this line, or equal, so solid line is fine. And we'll do our second one. I'll do green here for this one. We have our two intercepts. X-intercept is 4, and our y-intercept is 1, like this. So already, I think we can notice something about this situation as well. Okay, like that. And are we shading above or below this one?
Above.
We say above, okay? So let's not make the same mistake we had last time. Let's test a point here. So we're saying the point 0 and plus 4 times 0 less than or equal to 4. So 0 is less than or equal to 4. Is that a true statement or a false statement about the origin here?
True.
So where are we shading?
Below.
Below. So we have to include the origin. Okay, so there is our area. What do we notice about these two? What do you notice about
They
the
are
line? Go ahead. Go ahead.
overlapping.
Okay, so overlapping. Almost all inequalities will overlap at least somewhat. What do we notice about the lines themselves?
Perpendicular?
Are
No,
they
parallel?
I don't know.
parallel? So both okay, so they're both parallel. Same situation that we had last time. Parallel lines here. But last time they didn't overlap at all. What do we notice about the relationship between these two here? the solution area. What will the solution area look like? What is it the same as?
Below the second line.
Right, so the solution area is just the same as the green shaded area below our second inequality, because the green one is fully inside the pink one. It's not mostly inside, it doesn't ever leave or anything. So this green one is fully inside the pink one. So we were trying to graph and show a system of inequalities, but really, even without the pink one, the area, the shaded region of the two together would still be the same, because the green one is the limiting factor and the pink one, that extra area between the pink and green just never comes into play. So basically, the green one alone is enough to define the shape and the area that we have. So these are the two special cases that can happen if our two inequalities are parallel. If we have just lines that are parallel, there's only one thing, just no point of intersection. But then with inequalities, we have a few extra things that can happen. Okay, let's move on to our application question here. So we are doing an application with systems of equalities and trying to visually represent a situation, a scenario, and then also try to answer some questions about it. So take a moment and read the problem that's here, and then we'll talk about it. Okay, let's try to talk about this. So the question is already telling us that this is a system of inequalities. What variables would you choose here? Or how would you represent the situation with variables?
Can we use X for the protein calories for protein bars? The amount of calories he wants to use for protein bars with X.
I don't think that, something about protein bars, but I don't think the total number of calories would be what we want.
Maybe just number of bars.
Okay, so number of protein bars.
Yeah.
Let's call that P. So P will represent number of protein bars to eat. All right, and then the other thing that we have in the situation?
J.
So J for number of, I don't know, cans of juice, bottles of juice, whatever the unit is, number of, I don't know, juice units, juice things. So they haven't told us here. Okay. So we have our two variables. So it looks like we want to create some equations and or inequalities to represent this scenario. What could we do here?
140p
140p
plus 125J
125J
is greater or equal to 1000.
1000. So greater than or equal to 1000. All right, let's think about this and just go back, look at our problem again, make sure it makes sense. So number of protein bars, or the number of calories in one protein bar is 140, and we multiply that by number of protein bars, so total calories from protein bars, and then also number of calories from juice units, juice things, times number of juice things will give us total calories from juice. Okay, and we have this target here of 1000. Do we want to be, so 1000 is a key number, but do we want to be 1000 or more or 1000 or less? And it's telling us at least. So just think, more than 1000, is that okay? Yes. Exactly 1000, is that okay? Yes. Less than 1000, is that okay? No, he wants to add at least 1000. So, because he's exercising or something. So less than that is not going to work. So greater than or equal is the right way to represent this. All right, let's do these. Can we make another inequality here?
Yeah, 1.80p plus 1.25J is less than or equal to 12.
Less than or equal to 12. So protein bars cost $1.80 each, and times number of protein bars will give us the cost there. Same for J, and then less than or equal to 12 because he doesn't want to spend more than $12. So spending exactly $12 is okay. Spending less than $12 is great, but can't go over. So must be less than or equal. All right, looks like we have two inequalities and we just want to turn them into a system and then graph them and show the area that represents the two together, the solution area. So let's do that. I have that written out here. Let's do our two intercepts method to be able to graph this. Trying to remember what colors I just had there. I think I had, it doesn't matter, choose new colors. Okay, so we'll do orange for the first one. What are the X and Y intercepts for this?
7.
Or sorry, P and J intercepts, let's write that here. So let's say we're going to, sorry to interrupt you, but we'll have, we need to label our axes carefully here. So P instead of X, why can I not choose the right tool? P instead of X here, and then we'll have J instead of Y up here. Okay, that's better. Sorry, can you tell me again for our P intercepts and our P intercept and J intercept?
The P intercept is 7.14.
Okay, P and J, so 7.14.
Okay. And J is 8.
Okay, the 8s I can see 1000 divided by 125. The 7.14, is it exactly that, or are there some more decimals there?
After 4, there is 1, or there is 2.
2. Okay, so there's more. This number probably goes on forever. But looking at the scale of our graph, and if we remember for our variables here, like P cannot be like 0.001 or something. Like P, it's number of protein bars. It's 1 or 2 or 3. They must be whole numbers. So we don't need to be this precise probably with our number, just 7.14, probably good enough. We could go further though. You know, long division, like 140 divided by sorry, 1000 divided by 140, and we just do, okay, that goes in 7 times this, 980, and then 20, and bring in another 2, and then decimal, and 1, and dot, 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 dot. I'm sure we all remember how to do long division if we do need it. Okay, and let's get our second one here. What are the intercepts going to be in this case?
6.666 and many sixes.
Okay, so 6.6 repeated.
And 9.6.
9.6 for the other one. Okay. All right. So again, if we wanted to do some long division to figure those out, that's what I did in advance here. I hope that's what you did too, instead of just jumping to a calculator. Let's put these on our graph. So the first one, orange one, we have P at 7.14. So hard to put this, the exact location, but it's going to be about here. And then 8, that one we can do precisely. And our other one, J 9.6, 9.5 is there. So let's just go up a little bit. And then 6.6 will give us about there. Okay, so those are the lines. We have a few different possibilities here. We did this in class a bunch of times, so let me just kind of jump to asking you the final version of this. Let's call this region 1, 2, this little tiny bit here, 3, and then up here, the rest of it above both of them, 4. Which region represents the solution space, the feasible region for this problem?
We don't know yet because we haven't figured it out with that symbol.
Symbol?
That greater or equal to. I
Okay,
guess.
that's what I'm asking you to figure out. So try to tell me this without me doing the shading for you. Look at the inequalities and see if we should be shading above or below, put them together in your brain and tell me which area we should be shading in.
1.
1.
I say 1. Everyone agrees 1? Okay. So if we're doing 1, that would mean we would have to be going below the pink one and above the orange one. So below the pink one and above the orange one. Let's start with the orange one here. If we just test the point 0, so that, it's not too hard to do the 0.00 here. So 140, 0 plus 125, 0. Basically, just put a 0 on the left and then see if it's a true statement or not. So orange one, if we use the origin 0, 0, then that would be 0 is greater than or equal to 1000. That's a false statement. So the orange one does not include the origin. We must be above. And then exact same thing for the pink one, except the inequalities flipped. So we must be below that. We must be below the pink line. And that gives us the shape that we have shaded in here. Okay, so that shaded area, I guess if we wanted to draw this in another way, what we could do is show it like this. With our linear programming stuff, we don't really do this, but with this kind of problem, this is another valid way of handling it. We could just draw our line there and there to the point of intersection. And then we can erase the part beyond it and just say, there it is. There's the solution space to this. We know for this problem, we didn't write it, but we understand that P must be greater than or equal to 0, and also our J must be greater than or equal to 0. The P one didn't really come into play here with this area, but J greater than or equal to 0, that's why we're not shading off in this area. That's why we're just stopping at the vertical axis, at the J-axis here. Okay, so there's our shape. The question was asking us, though, to find out about two particular spots. We didn't write the numbers on this slide, so let's just quickly hop back. So it's asking us about 3 protein bars, 5 bottles of juice, and also 5 protein bars, 3 bottles of juice. So let's see if we can do those. So first, 3, let's write this out here. So the 0.35, where again, this is P and then J. Is this point in the area?
Yes, it is.
So it does look like it. It's a pretty thin area, but our lines are, precise enough, and it looks like that's this point right here. And yes, that's possible. That is inside the solution space for the system of inequalities. The second one they asked us about was the reverse. 5, 3. Is that possible? Is that a valid solution?
Yeah, it is.
5, 3. That looks like this point right here.
It's not possible.
Yeah, this one is outside. It's close, but it's not actually in the solution space. Let's just do a tiny little extension on this. How many combinations are actually possible here? How many different ways are there to satisfy this, these two limitations?
Six.
5. 5.
We say 5. Okay. Tell me the coordinates of them that you're seeing.
P is 5 and J is 2.4 maybe. Like that.
So 2.4J. If you walk into a convenience store and you tell them, I want to buy 2.4 bottles of juice, what will they do to you?
They will kick me out.
They will. So that's not a valid solution. Just considering the math here, yes, but we apply this back to the real world context and then try to answer in that sense. So tell me other valid points
3.
here.
3 I have, like P is 3, J is 3, and sorry, J is 4, P is 3, J is 4, P is 2,
Whoa,
J is 5.
hold on. P3, J4 is this point right here.
No, P is 4, J is 4, like it
Okay.
will be?
Our graph is, that looks like it's outside. What we should probably do is take that point and put it into our inequalities and test. It may or may not be within the pink one, but if our lines are good enough, then it actually looks like that's not included. Can someone else tell me, you've had a few shots, can someone else tell me a valid point that they see here?
2 protein bars and 6 bottles of juice.
Okay, so the point's 2, 6. Tell me another one.
1, 7.
1, 7 up here. 1, 7. Any more?
1, 8.
1, 8.
And maybe 0, 9.
0 and 9.
And 0, 8.
0, 8 also. So 8 is like right at the limit. It's the intercept there, but it is included. So let's erase these ones. So it does look like we have, let's draw the last one. Definitely 6, maybe a 7th down here. If our lines are not perfectly accurate, it might be worth checking that one, but at least 6. I'm gonna say probably not that 7th point. So once we remember that we can only use whole numbers, then okay, there's only 6 actual solutions that are possible here. Okay, so that's just a little application of systems of equations and the visual representation of it with an actual word problem. Does anyone have questions about this? Okay, so now we get into the real fun part, the linear programming stuff. It's already 8:20, so definitely not going to get through all three of these. Linear programming questions take a while. So let's I'll throw this up quickly. So constraints are the limitations on our problem. Feasible regions are just, feasible region is the area that shows the solutions, possible solutions. We care about the corners of that area, that feasible region. ISO whatever lines, ISO profit, ISO cost, just showing our objectives and our method here. So this part is important. We're going to use this to solve it. So identify variables. What are the things that are variable, the things that we get to play with and manipulate and choose? What are the numbers that we can change? And then use those variables to represent everything else, the constraints and the objectives. We need to be able to talk about everything in the problem in terms of the same variables. And for us, it'll always be just two variables. So everything in terms of the same two variables. Then graph everything, then find the region, find the corners in the region, and find the corner that's closest to your objective function. If it's far away, then just shift your objective function a bit closer until you can see which corner is the best. Then we can do some algebra stuff to kind of verify exactly where that point is if needed. Okay, let's try this here. So this is the first problem. It is a bit big, can be a little intimidating to think about, but the slow, careful process, and we'll be able to get this. Okay, just read. We'll give you a minute and a half right here, right now, and just read it, try to understand. I'm gonna go get some water, and then we'll come talk about it. All right, let's try. It does feel pretty big and confusing at first. And we have not seen a problem quite this big in class yet, but we can do this. Does anyone have a guess or what they noticed and what they think we might do to start?
Make variables Z and S.
Okay, so Z and S. For Z will be sort of here.
Number.
Yeah, so these liters of this zombie drink. Liters of zombie, and S to represent the other fancy drink that they're making, the Sky Jack.
Professor, I think should it be 10 liters of each of the drinks?
Okay, yes. So it would work either way, but as long as we're consistent with it. But yeah, so the sort of 10 liters, I'm just trying to remember how I set this up on the next slide, just so I can be consistent here. Yep. Okay. So 10-liter units. 10-liter units. Let me erase this and try that again. 10-liter units of the zombie drink, and then 10-liter units of the other one. Zombie. And then same thing for this other one. Okay, so we've identified that. Let's think about all the different sort of other parts here, and then it will become a bit clearer as to why exactly we chose Z and S for these two things. All right, let's write this out. So first, this drink zombie. What is the recipe for this drink?
3 vodka, 6
All right, so 3 units vodka,
6 vermouth, and 1 ginger.
6 things of 6 liters of vermouth, and then 1 liter of ginger, I guess ginger flavored drink. I'm not really a fancy drink connoisseur, so not exactly sure, but the person who made this problem, I guess they are. The other one, Skyjack, what's the recipe for that one?
5, 3, 2.
Okay, so same thing, but 5, 3, and 2. All right, and we also have some limitations here. So let's write this as supply. What is our supply of vodka?
1,500.
All right, 1,500. For vermouth, it's the same thing. And ginger,
400.
400. Okay, so you, again, might be wondering why we're doing this. So we're just making a little table to represent all the different parts. Just take the words and turn them into some kind of data like this. Oh, we don't need vertical. So there is our setup here. Now, how does this help us? What can we do with this information now that it's in a table?
We can make 3 inequalities.
Okay, tell me what one of them would be.
3z plus 5s is less than or equal to 1,500.
Okay, 3z plus 5s less than or equal to 1,500. And we can see from the numbers, that's just coming from this vodka one. So there's a limit to how much vodka we have available to make, for this, whatever company has available to make drinks. So it's 1,500 liters. And so based on that, these two different mixed drinks that the company is making, that will sort of, that's how we are using up that supply. So one thing of Z, one kind of unit thing of Z takes 3 liters. So each time we make a Z, we need 3 liters of vodka. So 3 times Z. Each time we make one S, one thing unit here of Skyjack, then we need 5 liters of vodka. So these are the 2 ways that we use up this total supply. And the amount that we're using must be less than or equal to 1,500 because that's the limit. That's how much we have available. And then the exact same thing we can do for the other two. So vermouth will be 6Z plus 3S less than or equal to 1,500. And ginger Z plus 2S less than or equal to 400. All right, that is the setup. So that is actually the information. Sorry, there's one more thing that we need, but I'll just take a moment and talk about the variables, and then we'll add the last part here. So the things that we can vary, if we read the problem, the question is, how much of each cocktail should be made? So how many things of Z, how many things of S? Because those are the two cocktail drinks, the two types. That's the thing that we can play with. That's the thing that we can vary. We don't really, you might say, well, vodka, how many units of vodka we're using? Like we have this limitation. We're not directly choosing to use the vodka. Like that's not one of the drinks. The vodka just is required for this other thing that we are choosing. But also, we want to be able to represent the whole problem using the same variables. So the constraints plus the objective. If we can't talk about the objective with the same variables, we can't put them on the same graph, and this whole method wouldn't work. So we could make variables for vodka and vermouth and ginger, and then make some sort of inequality that looks like this, and then with this, and then our supply or equations there. But if we did that, we would not be able to represent our objective function with that same thing, or not in a clean way, not in any sort of logical way. So what's the objective function here?
15Z plus 20S equals profit.
Okay, so profits is going to be 15Z because they make 15 pounds of profits for each unit of Z, plus 20S. They make 20 pounds of profit for each unit of S here. So now it's set up. Now we know that we have everything right, because the same two variables, Z and S, can be used to talk about all three constraints and about the objective function. That is what lets us combine all this onto one graph and use this whole linear programming method. So that's the choice of variables is really key. If you can't get the variables right, then you can't do anything with the problem. So that's very important. Little just kind of hint for our purposes, if we have three variables, it turns into a three-dimensional situation, and it's much harder to deal with. Every problem of this type that we will do in class will be just a two-variable scenario. So you're exactly two, not one, not three, not five or something, exactly two. So try to find the two that can work to represent the whole problem. Okay, let's hop, yes, this is everything here. So I'll erase the graph, the rest is the same. So this is the setup, just written a little more nicely. And we remember these sort of non-negativity constraints. We can't make a negative number of units of Z or of S, so we just kind of add those little things in there to remember that that is the case. Okay, so now we can take this and we can look at our graph here. Move this over. It's kind of arbitrary. It doesn't really matter where we put the Z or the S, which one is on the horizontal axis or which one's on the vertical axis. I have just chosen to put Z on the horizontal and S on the vertical because I had to choose something, but we're gonna stick with that. So let's do this. Again, I'm just gonna quickly cheat and look at the colors I used on the next slide. Okay, just so I can match these up here. So let's start with the first one, vodka. What are the X and Y intercepts going to be for this?
500.
500 said.
500 for Z and for S?
Or 300.
300. Okay. And we'll do the next one, vermouth and red. What are the two intercepts there?
The 250
250
and 500.
500. Okay. 250, easy way of seeing that. So 1,500 divided by 6, that might feel confusing, but just convert it to, forget the zeros. 15 divided by 6, okay, that's 2.5. We can probably see that. And then just shift the decimal place 2 positions back to 250. All right, last one we'll do in green here. And these ones, this is easier to see, just 400 and 200. I'll just write these in for us. Okay, I'll put these on the graph and then we will, actually, while I am putting these on the graph, you can start thinking about what constant might make sense for our profits equation here. It should work on the scale of our graph, not be too small.
3,000.
Okay, just give me a second to put these on first, and then that will help us see what we would want there. So Z 500 and S 300. The red one 250 and 5. And green one is 4 and 2. Like this. Just make sure I got my colors right there. Yep. Okay, so there are our inequalities. Let's do the shading first too. That will help us understand why we would choose a particular value for the profit function here. So are we above or below these inequalities?
Below.
We are below, so less than or equal, we just imagine if we put in a 0, we would get 0 less than or equal to 1,500 and 400. So origin is included, so that must mean that we are below each of these. Let's do a different color, pink. All right. So below the blue one, but that doesn't really matter because we have to be below the green one as well and below the red one. So this is our region here. Let's do one more thing here too and do corners, and then we can come back to the profits equation. Tell me where the or how many corners and where are they?
4.
Okay, 4. Tell me what they are.
The S intercept, I mean 200. 200
Okay.
S. Yeah.
Yep, that's one.
200, 100.
So 200, 100. So the green and red lines.
250, 0.
Okay, that color is easier to see, so I'll do that one. So green and our vertical axis, red and green, red and our horizontal axis. You said there's one more?
0,0.
Okay. will that one ever be the best solution?
No.
Okay, so yes, in the geometry, it's a four-sided shape, so that is a corner, but for our purposes, we'll just wave our fingers and make it go away because we don't care about that. We know it will never be the best one. All right, so we have three corners. We want to figure out which of these is the best. So our profit equation here should be reasonably close to at least one of those corners. We don't want a profit equation that's really tiny, like down here in the corner. We also don't want it to be like way over here because that's just too far away. So we want it to be something kind of like this that gets close, or maybe it's like this and it's this corner. Maybe it's like this and it's the bottom corner. So someone suggested the number of 3,000. So let's do that. I'll write this below here. 15z plus 20s equals 3,000. If we do this, what will our intercepts be?
$600 and I'm sorry, not
200
600.
and
Sorry, 600 and
150.
150.
Professor,
200.
it will be 200 and 150.
Okay, let's try that. 200, 150. 200 times 15, 200 times 1.5 would be 300 times 15, 3,000. Okay, and then that's basically the same math in the other direction for this other one. So these two intercepts, what I am going to do, my strategy here is before we even touch the graph, we can just kind of look at these other numbers here. These intercepts should be just kind of in the middle, somewhere in the middle of these other points. So we want our profit equation to be, our ISO profit line to be above all of these. It should be outside of our feasible region, but this is going to be below all of these. So it's totally inside. So just based on that, not even looking at the graph, these numbers are too small. They're close, but a bit too small. What would your suggestion be for the next one?
12,000.
12,000, okay. So let's try that. If we do 12,000, so we did the math once to calculate the intercept points. After that, we don't have to do a lot of work. 3,000 to 12,000, that's times 4. So we'll just multiply all of these by 4. So that's 800 and 600. Okay, 800, 600, that's above all of them. Maybe a little too far above, but let's try it. 600. 800, I can't actually see the 8 because of my zoom controls. 6, 7, 8, I think that's right there. That looks a little too far away.
What if we make it 6,000?
Okay, let's
Yes.
try that. Let's do 6,000. If it's 6,000, that's double 3,000. So intercepts will be 400 and 300. Just write this out for thoroughness. 15z plus 20s equals 6,000. 3,000 too small, 12,000 too big. Maybe 6,000 is perfectly, or the perfect one. So 3 and 4. All right. From that, I know I always did green in class, but now it's brown. From the brown line, is it close enough that we can see what the best point is going to be?
Yes.
Okay. If yes, then we're done. We don't need to keep drawing more of these. We can just get close enough that we can find out what the best corner is. then the rest will verify with algebra and stuff. We don't need to keep playing with these numbers to get them super close. So I won't repeat it here. We already went through a few times in class all the logic about why it's only the corners, and then why it's not sort of in the middle of the feasible region. You remind me about the last part though. These three corners to the brown line, how do we figure out which one is closest?
We
200, 100.
How do we figure it out?
parallel line,
A
Not parallel.
perpendicular line.
yeah, perpendicular line.
Yeah.
Okay, yeah, everyone's getting those words mixed up. Perpendicular line. So we draw three perpendicular lines and we say, or we ask ourselves, which of these three is shortest? Which of those three? So if we say point A, point B, and point C, in this
B.
case, it's pretty
What's
clear
B?
it's going to be B. That's the shortest one. So that is where the solution is. So, and very conveniently off of our graph, we can actually see, just line up on the grid, we can see exactly where B is. So B is, looks like 200 and 100. All right, let's get rid of this extra bigger line here. So that's the corner that we want. And we think we have the exact location. Let's say we can't 100% trust our graph. What could we do to verify this 200, 100 point?
To substitute them?
We can't substitute because we don't know if these are right yet.
Drag the brown line closer to the.
Okay, that's if we are not sure if this corner is the right one. I'm saying we are sure that point B, corner B is the correct one, but we just aren't sure about the exact coordinates. Maybe it's 199 and 101 or something. How can we confirm that it's exactly 200 and exactly 100?
Maybe we can substitute all the 3 points to this 15z plus 20s.
That's how we could compare. I'm going to say we don't need to do that because that's what drawing the ISO profit line did for us. If we don't understand the ISO profit line thing, or we don't feel like doing that, then what we could do is say, we have 1, 2, 3 corners. Which one's the highest profit? Let's just check all 3 of them one by one in our profit equation. And it wouldn't be too hard to do. And we just say, okay, whichever one is the highest profit. But that's not what my question is. My question is, let's say we are confident that B is the best corner, but we just don't know what are the exact coordinates of B. It could be 201, 101. It could be 199, 101. It could be 19999.
Amazing.
Professor, we can substitute those numbers to one of the inequalities, I guess.
We can compare the 2 inequalities, like the green line and the red line, and find the point of intercept.
There we go. That's what we would do. So if this were just lines, then what we could do is take these points and just substitute them into the 2 inequalities we have and see if if it lies on both of them. But these are inequalities. They're not lines. So this point here, 199 and 99. So I'll just tell you that's not the correct point, but it would be valid. It would work with both of the inequalities because it's inside our feasible region. So it would come out as, yes, that's a valid point. Yes, that does satisfy the inequalities, but it wouldn't be the best one. So what we want is the intersection of the red and the green lines. That's how we're figuring this out. So just system of equations for the red line and the green line, do elimination, do substitution, whatever we want to do, and then that's how we confirm it. So again, this is a pretty simple scenario, and we kind of probably already see what the answer is going to be, but let's just write this out for thoroughness here. 400. Okay, that's our system. And let's solve this. What's your preference here? Substitution or elimination?
Elimination.
Okay, Z or S?
S.
S.
We want to do S. Okay, so if we're going to do that, then let's write this over here. So what are we going to do? Equation 1, equation 2. What are we going to do to eliminate?
Equation 1 multiplied by 2.
Okay, so 2 times equation 1.
And 3 times equation 2.
3 times equation 2, and that's 12Z, 6S, and 1,000. 3,000, and then the other one is going to be 3Z plus 6S is equal to 1,200. We are subtracting because we have the same sign on both of these. So 9Z 0S is equal to 1,800. And therefore, our Z is equal to
200.
200. Okay, so that's what we saw on the graph. And we could just quickly use the second equation. 200 plus 2S is equal to 400. 2S is 200. S is 100. Okay, so some quick algebra. We verify, yes, the exact coordinates of B are 200 and 100. So that's the exact points. And then we are being asked to find the maximum profit. So what's the last thing that we should do?
Substitute the coordinate into the profit equation.
Okay, good. So let's just erase this. And I'll put this over here. So profit equation 15 times Z, 200 plus 20 times 100. And what does that equal?
5,000.
5,000. So 3,000 plus 2,000, 5,000. Okay, so 5,000, this was pounds. So 5,000 pounds is our maximum. Max profits. And that max profit occurs at exactly 200 units of Z. So let's write it this way, where Z is equal to 200 and S is equal to 100. So there's the max profit, and there's exactly how to get it. Okay, so we did it. These take a while. That was 30 minutes. You guys were answering quickly, so we went through it quickly. But linear programming is not fast. So that is our solution in this scenario. Does anyone have questions about how we solve this and how this works and any kind of background theory stuff to this? Nope. Okay. I do have 2 more, and I think we would have time to get through at least one more. We would have time to get through one more of them. The next one is more complicated and also introduces or asks about a thing that we haven't actually covered in class yet, about the slack and tight constraints. The other one's a minimization problem, and we haven't actually seen minimization in class yet either. I think I can get through both of those in the second half of next week's workshop. So spreading this out is probably the better approach. I'm going to just say a little bit more about what we can see here with one of these, and then we'll just kind of call it for today. What do we notice about the blue line, the blue inequality, our vodka constraints? What do we notice about that relative to what we said our best point is, point B?
There is no intersection with this point. With this
Okay,
point.
there's no intersection, yeah. Let's try to apply this to kind of the real world situation, back to this drink manufacturing company. So they have this limited supply of vodka and vermouth and ginger. And the way to maximize their profit is to use this point represents here. It's on the limits. It's on these constraint lines for red and green for vermouth and ginger. So this point means use all available red, the vermouth.
Oh, they will have a surplus of vodka then.
There we go. So vermouth, use all available vermouth and ginger. So they're using all of those two things. They've pushed those limits as far as they can go. That's what the intersection of red and green means. But that also means blue is not sort of engaged. There's more available there. So if they wanted, they could, and again, so points, perpendicular line, this distance is representing the degree, the amount of extra vodka available. So this is the way where they make the most money or whatever. And this is the thing that they want to prioritize. And after doing this calculation, they realize, hey, we have extra vodka. If we want to use this extra supply of this one thing, the extra vodka for some other drink, sure, we have this many units available. When we do this in class next week, I'll actually, we'll talk about how we can calculate exactly that. It's not particularly hard, but they have a bunch of extra. So for the vermouth and the ginger, they say, no, no more extra. It's all going into this top priority thing. We can't use any extra in anywhere else. But if we want, someone else in the company wants to make a new thing using vodka, hey, we have this much extra available. So in a business situation, we might say, okay, this is our top priority. All available resources have to go into this. But then if we optimize like this, we can say, okay, sure, put everything towards this that we need, but really only there's a bottleneck. Only these two things are kind of limiting what we can do. And we have some extra of these other things, this other supply or labor time or whatever, we can spin those off to other projects. So that's a useful thing. Instead of just saying, well, put everything on this and don't make it available for anything else because this is priority. Well, okay, we only really need to maximize or use all of the red and the green one, the blue one, and the whatever other ones we might have. We have some extra, let's use them elsewhere. So that's a very useful thing for a business to identify, to be able to actually use all their vodka by doing something else with it as well. So I'll introduce the terms here quickly. The red and green ones, because we use all of them, those are tight constraints. Tight, because like if you're pulling a rope, it's tight, there's no more to pull. We are at the limit of it. The blue one, the other one, because it's like loose, you could pull it more, there's more to go, as a slack constraint. It's not been maxed out in the scenario. Okay, so that's going to be an important thing. We can see that here with this problem already, and that will be an important thing with the later problems as well. All right. Does anyone have questions they want to ask before we wrap up? Does it, okay, let me ask, does this kind of make sense? Do you feel like you are kind of seeing what this process is and why it works and how it's useful?
Yes.
Yes.
Yes. Okay. I hope most of you are feeling that. If you don't yet feel like totally confident that you could do one of these on your own, that's okay. These ones are a little more complicated. But this, where did we put them? This process. Just kind of keep thinking about this process, sort of remember this list of steps. There's more detail to it than just this, but this is the core part. If you can remember these parts, you should be able to kind of work through any one of the problems that we see. That's my alarm. I guess time to finish. So thank you everyone for listening. I'll see you in class next week, and good luck with the preview question. Goodbye, everyone.
Professor, I'm
Thank
sorry.
you.